All right, hello, IB Physics. Welcome. So today we are looking at 2-1. Welcome to the start of the new quarter. We are still doing unbalanced forces. So you're probably watching this learning instructions video right now. Good for you. All right. So we have two things that we got to do. Well, really one thing in class, but so it's 5.1. It's called the elevator lab. That's what we're doing in class. And then 5.2 is our homework assignment. So let's take a look at 5.1 that we're doing in class. So this is called the elevator lab. It looks like this. Okay, and there's a video that we also have to watch. Okay, so let's send this to Notability. I'm going to send it to IB Physics. I'm going to open the note. Okay, I'm going to say that this is the teacher. Okay, teacher. All right, so number 1. So we have a pre-lab here, which is kind of like, thinking about these questions, and we don't have to get them right? There's no expectations here. So it says, what is the force reading on a bathroom scale measures? So normally we think a scale, right, a bathroom scale, it gives us like 120 pounds or something, and we think that that gives us the weight. So we would think that gives us the weight, right? That's measuring the weight. But actually, that's a little bit of a misconception. What it does is it actually gives us the normal force, right? That's what a scale actually measures. So if you have a scale like this, well, that's a really badly drawn scale, but if you have a scale like this, what it's measuring is how much force is pushing down on it. And whatever force is, however much that is, it's going to read that out, right? So that's the normal force. And usually it's equal to the weight because we're not accelerating or moving up and down at all. Now, when we start moving up and down, then, all right, that's why it's called the elevator lab. Then the numbers gets weird, and we find that it's actually not reading the weight, it's reading the normal force. Okay, so that's a little bit of an explanation for why it would be normal force. Okay, second part says to draw predict the free body diagram. Stand a scale, elevator. Okay, so it wants you to think about the forces in the y direction. So if a person is standing on a bathroom scale in an elevator at rest, right? So we would think, okay, well, here's a free body diagram. We know there's Fg on it, on the person, and we know that there's Fn on it. So the question is, are these two equal to each other? Right, so yes, the person is not moving, right? So we know that F net is equal to Fn minus Fg, and then we know that F net is equal to 0 because the object is not moving. So we have 0 equals Fn minus Fg. And so we just move Fn over, right? So we just move Fg or Fn over, it doesn't matter. And we get, right, so we can move Fg over and we get that Fn is equal to Fg. Right, so we get the Fg is equal to Fn, or you can write it the way that I wrote it first, which is Fn equals to Fg. Same thing. Right, so that's what we get. Okay, so what about when the elevator starts accelerating up? Now, this is a tricky question because we don't know what's going to happen, but I want you to think about it like this. I mean, because we all have experienced elevators before, correct? And so here's Fg. So when the elevator is going up, right? I want you to think about this. If the elevator is going up, how do you feel, right? How does the observer feel, right? So in this case, when you are going up, you are being accelerated up, and what's happening is that you will start to feel heavier. Now, if you start to feel heavier, what's going to happen to Fn, right? So remember, if you apply a force going down and you start to feel heavier, right? So the force starts to get larger, right? What's going to happen to Fn? Now, Fn is always a force that reacts opposite to this force, right? To this force that we're looking at. So, as you can imagine, maybe Fn actually increases. Okay, which is possible because now, right, we have a situation where Fn is greater than Fg. Okay, so maybe, right? And it kind of has to be greater because we're accelerating, right? Like we're moving, so one of these numbers have to be bigger. It's either Fg or Fn. And in this case, we think Fn because, well, if Fg was bigger, then it would be going down, right? Like, right, it would probably be going down. But in this case, it's going up. So we would say that Fn is greater. Okay, so that's the logic or sort of thinking for this one. A little hard to think about. Okay, what about going down? So in this case, our Fg is the same, but in this case, I think that maybe Fn is going to decrease. Right, so I think that Fn is going to be less than Fg. Okay, so that's what I think is going to happen. Am I correct about this? I'm actually not super sure, but we're going to find out. Okay, so there is a video that you have to watch. Okay, so you want to click on it and watch that. Then, for each part of the video, you want to record the scale reading. Then draw a free body diagram for the passenger. And I want you to note that you do not have to do the like the predict, explain, observe, explain again, right? We just want the numbers. That's what we care about. That's what we're here for. We want the numbers. Okay? Now it says to, okay, and then it says circle the direction of the velocity, blah, 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 describe, and the acceleration vector that describes the motion of the person in the elevator. Calculate the net force. Okay, it wants you to take g to be 10 meters per second to make the calculations easier. Also, a reminder that the person's actual weight does not change, however, the scale reading does. Okay, and it wants you to note that 1 pound is equal to 0.5 kilograms. The scale in the video reads pounds, so that means we have to do some conversions, which is a little annoying. Okay, so I won't be able to show you the video because I'm recording, but what you're gonna find is that in the video, the scale starts at, I believe, okay, so I actually have the video pulled up, so I'm going to be watching it, but it starts at 124. Okay, so the scale is going to start at 124 pounds, which is about, so you're going to take 124 and multiply it by, where is it? Conversion, okay, 0.5. So take 124 pounds, you multiply it by 0.5 to convert it to kilograms, and then we get, let me do this real quick, 124 times 0.45, and that is 55.8. So I'm just going to call this 56. 56 kg. Okay, so that's the mass. Okay. Okay, so that's a mass. Well, okay, that's the mass. Cool. What's the velocity? The direction? Okay, so it's asking us to circle the direction of the velocity. So if velocity 0 has no direction, acceleration 0 has no direction. Here it's asking what's the net force going to be. Well, it's not moving, so it has to be 0. And the acceleration is not moving, so it's 0, right? Okay. So, wants us to draw and calculate Fnet. Okay, so here we have Fg, and then we have Fn. And we know that Fnet is going to be equal to 0. So we say Fnet equals Fn minus Fg. Now it's 0. So Fn minus Fg. And that's it, right? But if you want to write numbers in, you can write in 56 kilograms. Let's see, in this case, I want to do 56 kilograms times 10 meters per second squared, which is our acceleration due to gravity. and then here's our Fn. And our Fn is, well, our Fn is equal to Fg, right, in this case. So it's just going to be basically two same numbers. But whatever we get, so we get 556 newtons, right? So then the number over here has to also be 556 newtons. Okay, so then 0, 0. Okay, 0, it's all good. Okay, now it starts to get interesting when the scale starts reading something different. And what's really interesting is that when it starts going up, the scale reads about 130 pounds. Okay, so the person's apparent, this is called the apparent weight, okay, the apparent weight or mass starts to increase. Okay, that's kind of interesting. So I'll take 130 times 0.45, and in this case we get 58.5 kilograms. Okay, so I just did it on my calculator. You can do it on your calculator too. Okay, so the velocity is going up, and the acceleration is going up as well, right? So this person is being accelerated up, right? It has to accelerate in order to go up. So we know that the net force should be positive because it's going up, and the acceleration should be positive as well because it's going up. And so we have F net equals, whoops, sorry, I got ahead of myself. Okay, so we have Fg, and then we have, and I think, okay, and then we're going to say, in this case, we think that Fn is going to be greater than Fg, right? So this is the situation. Let's find out if that's actually true. Okay, so what's going to happen here is we have, okay, so what we want to do is we want to take our apparent weight or mass. I keep saying weight, but we want to take our apparent mass here. Apparent weight. I want to take 58.5 kilograms. I want to multiply it by 10 meters per second square. And this is going to give us Fn, right? Because remember, the scale measures how heavy you start to feel. And so in this case, it's going to measure like 585 newtons, right? So that's what we get. And then, right, so here's your F net. And we minus it by Fg, which is 560, which we got from over here, right? So here, okay. Okay, so we get 25 newtons, right? So you can see that, right? You can see in the numbers that Fn is greater than Fg in this case, right? So our F net is not equal to 0. Okay, so F net does not equal 0. Nice. Okay, so that is how you are going to do these problems. Okay, you're going to watch the video carefully, and then you are going to think about what direction the velocity vector is going, the acceleration vector is going, and if the net force is positive, and if the acceleration is positive or negative. Right, so in this case, if the net force is positive, the acceleration should be positive as well, which we can calculate, and that is what this problem number 9, is asking you to do. Okay, so this is asking you to, so it says, for number 2, when the calculator starts going up, when the elevator starts going up, you should have calculated that the net force is not 0, which it is, which it is not 0, meaning that there is an acceleration. So it wants us to calculate acceleration. If F net is equal to m times a, use the F net you found earlier to calculate the acceleration at that point. Okay, and the hint here is that ma is equal to Fn minus Fg. Okay, so how do you do this calculation? It's really easy actually. So what it wants you to do is, what is our m? Well, our m, let's see here. So m is 56 kilograms. Okay, so we know that our m is 56 kilograms. And we know, right, so we literally just calculated F net. F net is 25 newtons. Okay, So let's go back down. So we just calculated that F net is equal to 25 newtons. But essentially it's, okay, so it wants us to do, okay. So F net, okay. So F net, okay, so what I want you to see is this right here. So F net is this, right? So it says if F net is equal to M times A, right? So F net M times A, and then the 25 goes right here, right? That is what we get from doing Fn minus Fg. Okay, so Fn minus Fg gives us 25. So now we can actually calculate the acceleration. But you're asking, like, how? Well, you know what M is. So you do M times A equals 25 divided by M divided by M. So A is equal to 25 newtons divided by 56 kg or kilograms. And if you do this on your calculator, you should get, let's see, what do you get? All right, so you get 0.446 meters per second square. Okay, so that is our acceleration. Okay, there you go. So that's how you calculate acceleration. All right, folks, I want you to have fun doing the rest of these. They're different situations. Have fun. Okay, bye.